Good morning. Y'all survived the weekend?
Define survive. I had to fix 2 water leaks in my house. It was a blast.
Well, your beard's not cut off. I guess that's something.
Yeah, it's great. It's a great weekend.
Man, I was looking at the schedule. This is like we have this week and 2 more weeks, and this term is over. How in the world did that happen? Crazy. So also, I was looking at this week. We got a couple days of 4.5, which is kind of a neat topic. It's one of the reasons calculus was invented, which is optimizing things. And I'll show you a good example right off the bat in a second. And then we're using that, applying that to a kind of a neat project on Wednesday, and then a couple other applications Thursday and Monday. And then we're getting ready for a chapter 4 test. So anyway, clipping along. Let's share a screen and get after it. Cool. So the hard part of this section is just learning how to write equations for yourself. We got a little bit of practice at that back in related rates kinds of problems. And these are like those, except for not near as complex. But optimization really just means like what's the best value for something. And so that's just a reason to find kind of the top of a curve when it peaks over. And all there's a problem like this in your assignment. And this is one of the classic problems you could give that I'm going to kick off with here. So let's launch into it, shake out the cobwebs. 4.5, optimization is the usual title for this. So here's the typical example. Let's see, let's make it definitely rectangular. So let's see, let's give this some dimensions. Let's say, I don't know, let's go centimeters. Let's say this is 28 centimeters, and I don't know, this looks like less than half. So let's make this 12 centimeters. So you have this sort of rectangular piece of cardboard, and you're going to make a box out of it. And so in order to do that, you come over to the corner and kind of chop a little box out of the corner, chop a little square. Does it make sense? It would have to be a square. You're chopping a square out of the corner. So basically those are gone. And folding it then along these dotted lines. Folding it then along these dotted lines would make a box. And so I guess let me emphasize this is getting cut out. Those are gone. So just to give you time to kind of think about that. So then the end result, just roughly sketched, would be a piece of cardboard that looks something like this. So then if you folded it along these lines, if you folded it along those lines, then you'd end up with kind of an open top box. Does that make sense? So finally, it might look something like this. So what we're trying to do is, well, optimize this, or ultimately, I guess you might say, just max the volume. No, as I've often said in this class, like, I could just kind of show you how to write an equation. Some of you are sharp enough to just kind of write an equation for this, but we're just trying to find the maximum volume. And can you picture if X is really small, like X, and I'm going to say, let's not use X, let's use C for cut. Let's say that distance right there is C for the cut size. If C was like 1, then the box would end up looking kind of long and thin like this. So it'd be a nice big box, but then it just wouldn't be very deep. Whereas if you made C like 3, then you're going to get a box that's quite a bit shorter and kind of chunkier, if you will. Maybe something that looks more like that. So, the question is that long, really wide box, the really flat one, C equals 1, that cut size is 1 inch. Is that going to be the biggest volume? Is it going to be more like that because it's so wide? But well, then it's not very deep. But then C is 3 inches, is a whole lot deeper, but then the box gets a lot smaller. And so, which one is actually going to be the best volume? And so again, just to give you time to think about this, if you're naturally good at writing equations, maybe this comes really easy, but every question in this assignment is going to be kind of different. And so I just encourage you with all math problems just to play around. Remember, real understanding proceeds from the concrete to the abstract. In other words, I'm not really sure how to do this problem. I don't really know what's going on. I actually don't even believe that I'd get different volumes. Like, it's the same piece of cardboard. Why would the volume be any different? So, play. That's kind of my point. If you really want to understand things, play around a little bit. So let's do that now. Let's disappear this down a little bit. So let's play with C equals 1. Let's see, what would that look like? Well, does it make sense if C was 1 inch, then if I go back to this original picture up here, this would be a 1 inch cut and this would be a 1 inch cut. So the end result is I'm taking 1 inch and 1 inch off. And so this length up here would be 26 inches. And so my box would be 26 inches long because I lost an inch on each side. And then if I lost an inch over here and I lost an inch over here, that's 2 inches off of 12. Then that means this is 10 inches. And so my box is 1 by 10 by 26. And so you know how to optimize, what volume of a box is. That's not a terribly difficult formula. You know that volume is length times width times height in no particular order. And so in this case, the volume is a function of, I guess I'll say 1 is 1 times 10 times 26. And notice those are all inches. So you get inches times inches times inches, which is cubic inches, except for I said centimeters the whole time. So I got to go back and fix all that. I meant centimeters the whole time. Apologize for getting all excited. So that's not terrible, you might say. I get that. But again, not obvious. You have to think about that a little bit. So if I made some other kind of cut, then, again, you might think you're going to get the same answer. But you end up not getting the same answer. So let's think about that. All right, well, I think I'll reuse my same drawing up here and say, okay, well, what if I made a 3 centimeter cut on this thing? If it was 3 centimeters, then this is 3 centimeters and this is 3 centimeters. So I'm losing 6. So that means this length is down to 22 centimeters. But my box is 3 centimeters tall. It's really tall. That's the advantage. Over here, if I'm losing 3 centimeters on this side and 3 centimeters on that side, I'm losing 6 from 12. That means this only remains to be 6 centimeters. So now my box is volume as a function of a 3-inch cut is 3 times 6 times 22. Let's see, is that the same thing? So, the conclusion could be it doesn't make any difference. It's like whatever size box you want to get. So 3 times 6 times 22, but I don't get the same size box. I get 396. So by playing, you might determine maybe for the first time, oh, I guess it does make a difference. So obviously taller Taller boxes do better. I guess that one was too flat. That doesn't really work. So you could just keep playing around. You don't need calculus to do calculus. You could just keep playing with this. Guess, check, guess, check, guess, check, and maybe that cut will be a whole number. Maybe we're lucky and it'll be 3 centimeters. Maybe we've even just guessed it. Maybe it's 3 centimeters, but it could be 4 centimeters, or it could be 2.89625 centimeters. So in a sense, if we wanted to get it exactly right, it might take forever to guess. So the idea is at some point, can you not have to guess anymore? Like, can you make an equation for this? Can you, and some of the questions in your assignment then will ask you to say, okay, now can you actually step it up and find the function v of c, not v of 1, not v of 3, not do this. This is what mathematicians are sort of, this is what the only value we really provide is saying, let's not guess. Like, you don't have to guess. But can you do with C what you just did with 1 and with 3? I mean, that's the idea here. And so it isn't hard to write equations for yourself, but you do have to play around. You can't just stare at this and immediately write equations. Again, unless you're sharper, unless you're really natural at this. And by the way, I wasn't. Like, I'm a math teacher now, I know this stuff really well, but it's like I had to play around with this. This isn't obvious to me. Writing equations for yourself is usually one of the hardest things for students.
Would it be like something like C times 2C minus 12 times 2C minus 28?
Yeah, I like how what I often say is you're conjecturing. In other words, you're saying, I think and I like your tone of voice, like, does this work? Do I have this? So let's just go play around with this. If I go back here and I put C in for this is length C and this is length C. Then isn't our box going to be, if I kind of redraw it over here quickly, if our cut is C, then isn't our box C centimeters tall? So just like here there was a 1 and here there was a 3, then here there's going to be a C. And this is, now I'm to where I think Justin was conjecturing. What do I call this distance over here now? Since I'm taking C off of it and C off of it, then how long is it going to be?
28 minus 2C.
28 minus 2 C's.
I think I was saying it backwards the first time.
You said 2C minus 28? Mm-hmm.
Yeah.
So this is times 28 minus 2C. And then doesn't the same thing happen over here? In other words, if this is C and this is C, then isn't that width right there 12 minus 2 C's? So now what I have is actually an algebra equation that tells me the volume no matter what C is, which is kind of cool. Now again, let's just continue though with, I don't know, kind of the guess and check approach. 28, 12. So
And it makes sense when you multiply all those together, you'd get a cubed equation.
yeah, you get a cubed equation still. So let's see if I can even say volume as a function of, I wonder if it'll even let me use C. Let's just try it. I was going to say X, but let's just try to stick with the letters we have and see if Desmos will let us do it. C is not a good choice because I have to go hunting for it all the time, but 28 minus 2C, close parenthesis. I'm going to turn the graph off just for a second. You'll see why in a minute. 12 minus 2C. And so now I'm going to pick C to be some number. Well, let's start off with what we saw a second ago, just to kind of make sure our evil plan is working. Let's see, is it liking it? It's throwing up a question. It's throwing up something up there saying it doesn't like this, and we'll see why in a second. I don't know. It's fun to play around. So it doesn't like that. It doesn't like V of C. Does it say why? You can't use C as a parameter of this function because it's already defined. Why can't I do that? If I say C is 1. Because it becomes V of 1. Why can't I do that? I'm lost.
Yeah, I don't know. That's a good question.
Well,
Maybe
I think to have a whole function like with the graph, you have to have C be continuous or
Yeah, it can't be a constant, in other words.
yeah, because then that would just be a point.
Would
Yeah,
it make a difference to do f of c like a function?
that's what I'm wondering. I'm wondering if I change that C to an X, that kind of a thing.
Yeah, I know I've tried like G of X and F of X, but I never tried doing it the other way around.
Because, yeah, I don't know. Let's just play. I mean, I'm doing this live just because I want you to see that sometimes it isn't set up for what you want. So I wasn't looking up, but I think that was Logan that said that. Yeah, as soon as C is 1, does it make sense? It's now V equals 6 or something. Well, a second ago we said V was equal to 260, right? So now it's not a graph anymore. But that's okay. I didn't care if it wasn't a graph. So anyway, that's whatever. Fine. X. Let's see if this is the answer. Yeah, I guess that works. So notice I said I want C to be 1, and then down below I said what's V of C, and it said 260. Isn't it? You see how it's working? Like I'm sort of checking to see if my function that I made a function for volume as a function of the cut, and I'm testing it out. And notice when C is 1, I got 260, and that's what I got just a second ago. And let's see, when I use 3, I got 396. Hey, this function is working. Do you see what I'm saying? But now what am I going to do? Like, why did I go into Desmos here? Somebody tell me, why did I go put this all into Desmos?
To find the maximum.
Yeah, does it make sense? And how am I going to do that? Does it make sense that I can go ahead?
I was gonna say when F prime equals 0, that's definitely a maximum or a minimum.
Yeah.
V
So watch how I sort of have, and this is the beauty of algebra. Does it make sense? I have all answers now. So what am I doing? Well, I'm just staring at the volume down there, and I'm not doing calculus yet. That's the thing I want to remind you. As I've said in this class, because of the technology that you live in, the day in which you live, you actually don't need calculus to do calculus. Does it make sense? I can just drag this along. So our previous record was 396, and notice it's going over 400, 40. Oh, there it just went down. So 402, 403. Is that it? 2.6. So would you agree that's darn close? And close enough for somebody that was actually building this box? Like, does it really need to be 4.21795 or whatever? I don't think it needs to be quite that accurate. So again, I think I can play around with, I don't think I've showed you this, but I think I can play around with that step right there so that now I can slide it a little more accurately. And it doesn't seem to want to do that. So I won't spend any time with this, but so when I picked 2.61, I think it was 403.11. So I wonder about 4.60, 403. Yeah. So would you agree that's even better? 4.30, 403.11. So accurate to the 100th place. I have the answer right now because it was smaller at 60 and it was smaller at 62. And so there's the max. I found it right now. So I'm looking for the maximum volume. And so beautiful. So I could have just guessed and checked, but you notice, I don't know about you, but I might have thought back here, if I spent some more time with this, that, hey, look, I got 260. And then when I made it bigger to 3, I would have said, hey, look, it's got way bigger. It's like 100 bigger. Awesome. I'm going the right direction. My next thing would have probably been to try C is 4. And then I would have been, if you will, now that I made the graph, I'd have been disappointed to realize, no, that isn't the biggest. And as a matter of fact, it turns out I actually passed the biggest one. The biggest one is actually before 3. I didn't know that. And that's kind of the idea here. And so, of course, where we're going with this, because you do speak calculus a bit, is if I turn the graph on for this, again, you should stare at that and you should actually know what you're looking at. This is a measure of Math 111. You should look at that at first and go, what? I don't get it. But then you
Parabola.
should look at the equation. What's the equation up there? V equals what? What kind of an equation is that?
Cubed.
Cubed. So therefore you should be looking for kind of an S shape, right? Now, again, this is where the guessing and checking comes in, because a second ago, what kind of a domain and range? And this stuff is always taught in a way that doesn't help people actually do anything. Notice our domain and range. Our domain is like, what size cuts can we make? And by the way, there's a limit to that. What's the biggest cut you can make here before you screw the whole thing up?
12.
Even less.
6.
6, because if you cut 6 off here and 6 off here, notice the entire 12 is gone. So you actually have to have a cut smaller than 6. Now 5.9 would work, but you got to make a cut smaller. And so your X's, your C's are less than 6, but what kind of V's are you getting at? Well, notice they're huge, 260, 396. In a sense, you should say, well, of course I don't see it because I've got gigantic Y values. Now, playing with that, you could even do this the really intelligent way. Rather than just zooming out, I could go to this little wrench up here in the corner and say, what kind of X's do I have? Well, I need positive cuts that are between 0 and 6. And I already played around to see that my maximum volume was like 411. So I'll say, I don't know, 412. So notice that's kind of the smart way to adjust the domain and range. And that's what domain and range means. Is domain is like, what inputs do you have? And then as a result, what outputs, the range, what outputs come out. But notice by playing around with it, well, yeah, of course, it's a cubed equation. Cool. But
Man, it'd be interesting to know what that box looks like once it goes below the x-axis.
yeah. And notice this is an interesting part of domain because the cubed equation goes forever. And yet if I was going to kind of limit it to the part that made sense in this problem, I'm not going to type this in, but I'd go to the end of this. Remember the bracket thing I showed you? I'd say, I want X to be between 0 and 6, because if you make no cut at all, X is 0, you have no box. If you make a cut of 6, you have no box. So it actually has to be between 0 and 6, which really means if I did graph that, all I would see was sort of that, well, frankly, it looks like a parabola, doesn't it? You're only that part of it actually makes sense in this problem, because you can't cut more than 6. And if you do, you get a negative volume, which of course isn't real. But of course, where are we looking? Well, we're looking for the biggest Y value possible. Well, isn't the biggest Y value possible that peak up there? And so the idea behind calculus is, don't sit there guessing and checking all day. I mean, again, we have a graphing tool, so we don't have to guess. And again, I just want to remind you, it's like you're in Desmos right now. Desmos wants to find those maximum points. See how it just found it for me? And I can click on it and it graphs it. So I mean, that's technology that allows me not to have to know calculus, which is really cool. And your graphing calculator does the same thing. It has a maximum function. So you can find that by, as I think Justin was alluding to earlier, by taking the derivative of it and setting it equal to 0, because that maximum is found because the slope is equal to 0. So it's actually calculus that allows you, I guess you could say, to algebraically find this and not have to ever kind of draw a picture of it. But again, you should be checking your work. And so notice by playing around, the 2.61 that we guessed wasn't the right answer, but it was, you can tell we were on it. But again, the right answer is probably 2.6118594, who knows how far that goes out. And we don't care in a practical context, but it's actually just kind of cool that you can get it exactly right. If you're a true mathematician, that gets you all excited. If you're more of a practical mathematician like me, you don't care. Like 2.61 is close enough. So That's kind of cool. So now let's do the calculus, because of course, you know, on a test or something, I mean, this is a calculus class after all. And as I said, there are certainly some cool points associated with getting this exactly right, not having to lamely guess, not having to draw pictures, not having to graph anything, you know, just go get it, go find it based on calculus. So to find the max, to find the optimization, to optimize the use of this piece of cardboard that you're chopping up and get the most out of the box, because you're going to put rice in it or whatever, to get the most out of it, we just figured out that the cut needs to be 2.61. And notice it's kind of cool that it came out some random decimal, like you never would have guessed it ultimately. Then of course, to find the max, I'm going to have to set max question mark. I'm going to have to set V prime of C equal to 0, right? Because isn't that going to give me the slope of 0, which is, as you already know, is going to tell me where that max is. Makes sense that I'd be setting the slope equal to 0. Well, what are you going to do to take the derivative of this statement up here? Are you going to say, hey, look, junk times junk times junk, I'm going to do the product rule? Or are you going to say, no, I'm going to multiply it all out. I'm going to multiply it all out. So there's a bunch of plus signs because derivatives like plus signs. I'm going to take that approach. I'm going to multiply it all out.
That sounds a lot easier.
Yeah, it makes the process a lot easier. If I did decide to do the product rule, by the way, I probably would at least multiply the C in so that I only had 2 things, like a double product rule with only 2 things to multiply, not 3. But I'm going to multiply the whole thing out. So let's see, if I go 28 times 12, and I'm going to save C for last. That'd be dumb. I'd much rather go 28 times 12 and kind of get that part done, get the hard part done, because then all I have to do is multiply by C. Where's my number? So 28 times 12 is 336. And then I have minus 2 times 28, which is 56. And then minus 2 times 12, which is 24. So I got 56 and 24. Those are both negative, which is 80. So I get minus 80C. And then I have minus 2C times minus 2C, which is actually plus 4C squared. But then I'm going to multiply them all by C, right? So then this is going to have a C, and that's going to have a C squared, and that's going to have a C cubed. And so there's my equation. And yeah, that's way easier to take the derivative of because it's now a bunch of plus and minus signs. And so I say, cool, I don't have to do the product rule anymore. So I do in this case, I think that was easier. So now I can take its derivative. Oh, that's an easy derivative to take. 336C is 336. 80C squared, the 2 gets multiplied by 80 and becomes 160. The C squared drops by 1. 4 times 3 is 12, and that's a C squared. That's interesting. If I set this equal to 0, doesn't a squared equation have 2 answers? Why is there 2 answers?
It's because it's still squared, so it's technically like the derivative graph would be a parabola.
Yeah, I mean, remember in the actual parabola or in the actual cubed equation itself, there is 2 places where the slope of that is 0, but we're just not going to be concerned with that one where the cut is 10 centimeters because there's no box. Like you get a negative volume. We're not concerned with that second one. We're after. So in this case, both answers aren't going to work. And you got to know that. Otherwise, it doesn't make any sense. So in a sense, it's kind of like, yeah, you should be not surprised that that's equal to 0. Again, you should be on your, if you're doing this on a test, you should be saying quadratic formula produces C is approximately, I'm going quadratic formula now. Be careful. What do you put in for quadratic formula here? What's A?
Well,
It's 12. Don't just do it in the order you see it. A is not 336. So if you need to rewrite it, then rewrite it, but don't screw that up. And because of my guessing and checking, I'm very happy because I already kind of know what the answer should be. And so it's kind of verifying the algebra. So I got C is sure enough 2.6. And I'll write 1149 and even goes on from there. And of course I could write this exactly. I could use the quadratic formula, and I could even say C equals, whatever it is, 160 plus or minus the square root of 512 divided by 24 or whatever it is. I could write it exactly. And I got the other answer that the graph showed me, which is 10.72. And of course, that one doesn't make any sense. So I found that, and as far as as far as this being a book problem, you could say, you could just be asked for the size of the cut. So you could say, and maybe the problem will say round to 2 decimal places or something. So you could say it's 2.61 centimeters, which we could have stole. But they may also ask what that volume is. Does that make sense? Like you might have to go back and find the volume based on 2.61, and maybe they want to know that too. And it was whatever, approximately 403, right? Cubic centimeters. So maybe you want to know both. Maybe you just want to know the size of the cut.
Yeah, it's like there was a problem on the 4.3/4 where it was like they had a graph and then it was asking for information from it, but it was saying, the graph is there just to help, guide what you're doing, but you still need to use calculus. And the thing was, you could get the answers from the first one off the graph, which I found out, but I was like, that's not good enough for me. I need to know why those are the answers. So I was like, I figured it out why it was happening. Like,
yeah. And that's kind of the beauty of this is, it's, as I'm sort of never ashamed to point out, you don't actually need calculus to produce these answers, which I think is kind of cool. So in your case, the reason I'm kind of always showing you that stuff as soon as I possibly can is just that you understand that you should not get these problems wrong and not know it. And you should be able to get the right answer, even if we did have to take a derivative and set it equal to 0, right? I mean, maybe we'll end up with an equation that's hard to take the derivative of, and maybe you screw up the calculus somehow. But again, I would love to see an answer on the test that says, I can see the answer to this is clearly about 2.61, but all my math is coming up with 3.12, and I don't know what I'm doing wrong. So again, what's this chapter really about? It's just like, in a previous, like in the very first part of chapter 4, we said find the maximums and minimums, and we just listed them as an ordered pair, but this is giving you kind of a reason to find that maximum. Notice in this case, you'd want to maximize the volume, but what if there was a formula that was involving cost? Like how much does it cost to produce a product? Well, then we'd want to minimize it, right? So it's not just maximums. That's why they use the word optimize, because you could optimize cost and then you're wanting something that's really small. So really what I want to do over a couple of days here is just kind of throw a battery of questions at you and just give you a chance to kind of play around with them. All very different. Well, let's try another one. Let's see, how hard is this? And I also know you have a question like this too on an assignment. So, and I would say this is more of just a interesting, playful example. I don't know why you would need to do this, but what if I gave you a parabola that sat, and I'll ask you the same, because I try to make up as many questions as I possibly can on the fly with you, as opposed to having them ready-made. Like, could you get a parabola to do that? Like now I need an equation for that parabola, you future math teachers. How am I going to get an equation that does that? Notice it hits right at 0, 0, and then it lands out there some other place. And actually, let's even be more specific and say it lands out there at, I don't know, 12. So I want it to hit at 0 and I want it to hit at 12. How do I get a parabola to do that?
you would do, well, you need to have x minus 12 times something else.
Yeah, remember, in order for it to have a 0 at 12, then it would have to have a factor of x minus 12, right? And to hit it 0, and then it would have to be x minus 0 or just x. And so that would do it. But if I multiply that out, I'd get x squared minus 12x. Does anybody know what's wrong with that? because I want the parabola to look like, why is the parabola I just found not going to match what I,
Oh, isn't that one going to be facing up like a U shape?
yeah,
We
it's a positive x squared. Its leading coefficient is a 1. And so you're exactly right.
need
It's
to
gonna be
reflect it.
facing up. So remember from the previous project I gave you, can't you multiply that by something if you want to? Like this expression back here, I could actually throw in any number there I want. So I could make that I could multiply by -1, which would flip it upside down. I could even multiply it by -2. What is -2 going to do? It's still going to flip it upside down, but what is the number? Again, I'm just hearkening back to the algebra knowledge that you should have. What happens to that graph if I multiply by -2? What happens to a graph when you multiply by 2?
It becomes steeper because that number is essentially the slope in the front that you're multiplying the whole thing by.
Yeah, that's right. So I can change, whether it flips upside down and kind of how tall it is by multiplying it by something, which is just kind of cool to understand. And so I'm going to stick a -1 in there. And so, you're not going to be asked on an assignment, they're just going to tell you. And so they'll say something like, here's your parabola, y equals, I guess that would be 12. A nice way to write it would be 12x minus x squared now. So there's the parabola. But again, that's for you future math teachers, like learn how to think. So, what is it? I'm great. You got a parabola, good for you. And remember that parabola continues, it keeps on going. But what I'm interested in is this rectangle right here. I'm interested in if I go to there and then I go straight across over to here and I go down to here, I want to max the area of that rectangle. So it's got to hit the graph. It's got to sit on the x-axis. It can't go below the x-axis. And of course, I can make where I have it right now, it's nice and wide, but it's not very tall. And if I move the point up to, say, here, let's go orange. If I move the point up to here, then it's going to be nice and tall, but now it's not as wide. And so, is there some place that rectangle could live in there that would actually give me the maximum area? And again, I just want to give you a second to think about this. How are you going to write? Last time we were trying to maximize the volume, so we needed a formula for volume. Some of you could write an equation for this right now. You could write an area equation that you're going to maximize. Others of you would need to play a second. Just play around a little bit. But I'm just going to give you a second to think about it before I answer it. So I'm going to start playing because I don't know how to write the equation. So I'm going to say this distance is 1. So this hits at 1. So I'm literally choosing the green rectangle. So it's probably not the right answer. Do you see what I'm saying? Like last time I picked the cut was 1, the cut was 3. It's not the right answer, but at least it allowed me to figure out what the heck is going on. So that distance is 1. Fine. Okay, well, let's see. If I need to know the area of this, I need to know kind of the length and the height, or the length and the width, doesn't really matter. But this is area and it's a rectangle, so it's just area's length times width. And so I got to know what those are. Well, notice the one doesn't really help me. Like the 1 isn't one of the lengths. Like what do I do? I mean, what can I do? What do I know?
Well, you know that there's 12 from 0 to 12 on that point, and if there's 1 on each side of the box, that would mean that the length would have to be 10.
Was Justin right?
Yes.
Yeah, he is. And that's because this particular graph is symmetrical. If this was a cubed equation, that actually wouldn't work. Could have put a parabola is symmetrical. So that's exactly right. So this distance is 1 and this distance is 1. So I guess that's at 11, I guess you could say then. So that distance is 10. Okay, so area equals a length of 10 times, well, how am I going to get the height right here?
Take the derivative of the equation and set it equal to 0.
You're stepping ahead. We don't even have an equation yet to take a derivative of. You're right. That's the
I
long.
meant to get the height, take the derivative of the y equation and then set it equal to 0 to get the max.
Gotcha. Even easier than that.
Would just be the y coordinate of the graph. So we
Yeah.
could just plug in the equation.
Yeah, you don't even have to take a derivative to get this. So this is the essence of what algebra really is. And so we got our length by saying it's 12 minus 1 minus 1 or minus 2 ones, I guess. But our width is just going to be found by plugging 1 in. In other words, if I take y and I put 1 in for x, like then I'm going to get the y. So it's the y coordinate. So if I put 1 into that, 12 times 1 is 12 minus 1 squared. So it's just 12 minus 1, it's 11. So that's a height of 11. So this is 10 times 11. And again, this doesn't have units, but that would be 10 inches and 12 inches. So the area would be square inches. So I got an area of 110. And again, maybe I got lucky. Maybe that's the right answer. Maybe that's the biggest rectangle I could possibly get. But I had to think about that. I had to reason about that. I had to wonder about that. And again, understanding proceeds from the concrete to the abstract. I can't just write an equation for the area here. Maybe that's too hard for me. So can't I just play around a little bit though and like try some practical questions and see what I can come up with? Okay, cool. So let's do this again because I kind of got it, but I'm not really very sure yet. So let's locate this one at 3. So that'd be 3 in. So that means the right side would be 3 in. So I think this one is at 9. So for that situation, then my length would be 9 minus 3, it'd be 6. Is that right? My length would be 6. And then my height, or my width, I was calling it width. My width is y with 3 plugged into it. So that'd be 12 times 3 minus 3 squared. So that's 36 minus 9, which is 27. Is that right? 27. So then my area is length times width, which is 6 times 27. My magic box says 6 times 27 is 162. So apparently the green one was not right. Like this is better. We have a better answer right now. So it's taller and thinner, if you will. So again, if you're guessing, like last time, am I going in the right direction and I should keep going? Or did I already pass the right answer? Should I go back to 2 or should I keep on going to 4? And again, just to give you a chance to think, I'm going to even do one more guess this time. Because did you notice it took me a lot more trouble to kind of figure out the first guess, but then the second one went pretty fast, and I bet you this one goes really fast. And so now I'm going to say, let's go clear out to 4. Again, my drawing isn't necessarily to scale. So if that's 4 and this would be 8, so I'm at 4 and 8. So let's try that one. So my length would be from 4 to 8 is 4. And if I put 4 into my equation, that'd be 12 times 4, which is 48, minus 4 squared, which is 16. So 48 minus 16 is 32. So my area is 4 times 32, which is 128. Again, isn't that kind of cool that we now have sort of 3 guesses at this? But 162 is better. Like I went to 4 and it's like started going back down. So I know for sure I went too far now. Is the answer between 3 and 4 then? Well, we still don't know that. Could be, but it could actually be before 3. So again, this is just kind of cool. You know, what's the best rectangle? Is it tall and thin or short and wide? The answer is it's like somewhere in the middle, and that's kind of what happened last time. It's somewhere in the middle. Well, maybe now, if before you could write an equation for yourself that you can take a derivative of and set it equal to 0, maybe you can do it now. What if we said, okay, fine, I'm tired of guessing, so I'm going to call this location here, and I'm guessing it's going to be before 3. So I'm going to call that G for guess. Algebra is where you say, can you do the same thing with G that you just got done doing with numbers? Can you do the same thing with a letter you just got done doing with a number? That's all that's involved. Since I can't read that, I'm going to go back and rewrite it. So then down here, I'm going to say, great, what did I really do? Well, let's see, I got to think a little harder now, don't I? What did I do to get my length? So this was 12. If that distance is G and this is symmetrical, that distance would also be G. Then I guess my length in here would be 12 minus 2 G's. So that's kind of interesting. That coincided with something we did before. So my length is 12 minus 2G. And if this is G, then my width was Y evaluated at G, which doesn't really accomplish much other than to replace the X with G. So what did we do with those 2 numbers? Every time, what did we do? We took the 2 numbers and multiplied them. So I'm going to do the same thing here. So now I can say area equals length, which is 12 minus 2G, times the height, which is 12G minus G squared. Wow. You see what I mean? Like, are you sharp enough? You could have just wrote that from the start. Again, there's probably 2 or 3 of you that are. But I wasn't one of those. I had to work at this. I had to think about this. But it's actually not that hard to write an equation for yourself. But you got to practice. Does that make sense? I mean, is that any different than anything else in life? If you want to hit a major league pitcher's pitch, then you better start in little league. You can't just walk out there. You might get lucky on a time or two. But that's all I'm saying here. Like play around a little bit. Not only does playing around allow you to write this equation for yourself, but you already have an idea of what the answer might be. Does it make sense if you do all this math and you get L is 4.2, you know that can't possibly be right because you just picked, because when we did 4 a minute ago, we got 128 and we had 6 as a choice and it was way better. And so, you know, we already kind of have a sense of what the answer might be. So when our guess was 3, when our orange try was 3, that's our best answer so far. So 3 is probably not the right answer, but it's around 3 and it's certainly not 4, certainly not 1. So my guessing also serves to kind of help me check my work. Of course, now that I have an equation, and this is the kind of thing I'd want to see on a test, that's the kind of thing you're going to want to see in your assignment because this is calculus. So you could guess and check here for another 30 minutes and have a pretty decent answer and never do any calculus. But in order to not have to guess, you got to be able to write this equation down because then you could go to Desmos or your graphing calculator and cheat and look for that maximum point. But you don't have to cheat because you understand that maximums and minimums happen when derivatives are equal to 0. And so I could just take the derivative of this and set it equal to 0. So you've got to be able to write. And I kind of like, you know, not just calling this A, but A as a function of G. That's kind of cool to say that because it's, you make a guess as to where you think that point is located. And now you have all of them. You have every area of every guess you would make. And if you want to test this just to make sure A second ago, we said when the area, when we chose 1, when our guess was 1, we got an area of 110. So shouldn't this function, if we haven't screwed it up, test is a of 1 question mark really equal to 110? So I'm going to type that in. 12 times 2 minus 1, that's 12 times, and multiply it out. Sure enough, it is 110. So okay, good, it's working. I could test it again for 3 because I knew that answer. Make sure that's working. But of course, what I want to do now is take the derivative and set it equal to 0. Again, what are you going to just say, well, that's only 2 expressions. I think I'll just do product rule. Or are you going to say, nah, I think I'll multiply it out. I think I'm going to multiply it out. So if I go 12 times 12g, that's 144g. If I go 12 times g squared, there's no such thing as math with letters. It's 12 times g squared. I go -2 times +12, I get -24g squared. And then finally -2g times -g squared, I get positive 2g cubed. Oh, I get a cubed equation. So again, this is, I didn't know that was going to happen, but I get some kind of a cubed equation. And I can collect the squared terms together before I take its derivative. So 144g minus 12 minus 24 is minus 36 plus 2g cubed. And now I can take its derivative, which is easy because it's just the power rule. And I can say, when is that equal to 0? And again, it's going to have 2 answers. And so I quadratic formula those 2 answers. My A value is 6, my B value is -72, my C value is 144, and I got 2 answers to this. Quadratic formula says G is approximately 9.46, and G is approximately 2.535 or 2.54. Which one is better? They're both good. But one of those doesn't make any sense. Do you see that? We haven't looked at the graph. If you look at the graph, you can cheat and see that one of them doesn't make sense. But in the context of our problem, what's the furthest I can go over?
Six.
Yeah. In other words, if this is at 12 and this is at 0, then to make a box at all, don't you have to stop short of halfway? So my guess has to be less than 6. And so on the cubed equation this produces, that must be that minimum down there again. So it's like it's outside of the realm of things that make sense. So notice, 2.54, that's really cool. Like, back here we saw that when our guess was 3, the orange one, we had 1.62, and we were wondering, is it between 3 and 4? And the answer was no, it's actually before. Is that right? It is between 3. No, it's before 3. So if we'd have tried 3.5, it would have not been as good, and we would have eventually guessed. But that's kind of cool. We didn't have to guess. And of course, if you're sharp enough just to write this equation down from the start, then you never have to guess at all. Well, we at least had to guess around a little bit just to kind of make sure we even understood how to write the equation for ourselves. So I found the maximum area rectangle at G is approximately 2.54 inches or whatever. And again, I find it satisfying, if you will, to go into Desmos or, graph this and make sure that that really was the case. Watch it happening. I don't think I'll redo that here just in the interest of time, but it'd be nice to slide along with different guesses, having this black equation as our base equation. It'd be nice to kind of slide along and sort of see, oh yeah, look, the graph really does peak right there. And oh, look at the different areas I'm getting, am I getting these orange and red and green areas, 110, 162, 128, and sure, does it really look like that max is a little to the left of that? How's your brain? Is it in pain?
I was gonna say, I like the guessing and checking. Like, I looked at it initially and I was like, I can't write an equation for that. But then once you guess and check once, you can look at each individual component and then, then put it all together, make a relationship between them. But it goes to scramble pretty quick trying to look at the relationship between all the stuff. So
Yeah, really well said. Really well said. And Logan, by the way, is really sharp for the rest of you. Logan's really sharp, and he's saying it's like I got to do this, and so do I.
throw me under the bus. No one likes the nerd. I did take this class before, but that was in 2013 and I got a C in it. So,
Yeah,
but there's some
in
stuff
the
still
spirit
left.
of full disclosure. That's good. Yeah, this is hard stuff. And this is why, like, this is one of the topics that makes people either get a low grade or flat have to retake this class. Because if you don't play around with these problems, then you'll never get it. Now, what math teachers can do to make this easier on you is they can say, okay, here's 2 problems I just showed you, and then I give you an assignment with only those 2 types of problems, and then when I give you a test, it's only those 2 type of problems. And then you can like study and memorize your way to do it. But you can appreciate, especially that second question, is anybody ever going to ask you to do that in the real world? No. Like, why would you have a square or rectangle that's sitting under a parabola? Like, that's not practical. That's not a practical problem, I guess. At least I can't think of one off the top of my head. So really what you're trying to do is, learn how to think here so that you can apply it. If it's business and you're kind of like, well, we could spend this much money and buy a nicer machine that'll produce the product faster, but then that costs us more. And, like, which one makes the more sense? I mean, are you the person at the business that can come up with some kind of a way to calculate, which machine? Buy the cheap machine, buy 2 cheap machines, and we'll actually make more money, because that's the issue, right? 1 nice machine, 2 cheap machines. Which one makes more sense? Productivity of employees. Do you let them work 4 10s? Do you have them work 4 8s, 5 8s? Do you 5 8-hour shifts, or do you let them choose? I mean, in the end, what makes people the most productive? It's like, that's the kind of stuff that this is about. You're trying to optimize the resources you have, and money and people and so forth. Like, will you be able to play around with that and like try stuff and come up with a way? I mean, it's not going to be like, none of the questions I assign in this section or in any calculus book they're never the real practical questions. That's kind of what I'm getting at. So again, as always, I'm trying to teach you how to think here, not how to get this question correct. So to that end, let's do one more question. And I'm going to give you some think time on this to see how much progress you can make entirely on your own. This is kind of a cool geometry question, I think. Max volume cone. No, let's do max volume cylinder. There's a few different ways to make up kind of neat problems like this, but here's one of them. So I have to give you some constraints, right? Because if I just say, what's the biggest cylinder you can make? So I'll just make the biggest one possible, but I'm going to give you some constraints to it. And I'm going to say, let's make the cylinder fit inside this cone. So what that means is you could have a stupid. That means you could have a cone that was, a cylinder that was, like, what if you said, well, I need a big cylinder. Let's have a nice big cylinder. So there's the bottom of the cylinder, but notice because you made it so wide, it hits the top right there. So you have a nice wide cylinder that isn't very tall. So you say, no, I want a tall cylinder. Nice and tall. Cool. Nice and tall. But as a result of being nice and tall, it doesn't have a very large radius. And so, again, is there some kind of a middle in there? Well, I have to tell you something about the cylinder. So kind of the constraints. So let's say this. Let's make this cylinder, I don't know, radius 6 inches, and let's make its height. Let's not do it that way. Let's make its height 18.
The radius of the bottom of the cone.
Yeah, the cone.
Okay.
So the height of the cone is 18 inches and the radius of the cone is 6 inches. And so that's the constraint. That's the cylinder. Obviously you'd want the cylinder. So, the question would be, what's the maximum cylinder that can fit inside the cone? Notice I have it touching. You'd at least want it like jammed as tall as you can possibly get it. But again, don't you find yourself looking at that thinking, I have no idea how I would do that. But I'm saying, guess at something. The red cylinder, the red cone you're stuck with, like it's a certain size, you're stuck with that. But you can do anything you want. So guess at something.
So the volume of a cylinder would be like pi r squared times the height, right?
Yeah, so let's just write ourselves a couple formulas. Volume of the cylinder is pi r squared h. And the volume of a cone is 1/3 pi r squared h. But notice the height of the cone is 18, but the height of the cylinder is not 18. The height of the cylinder is shorter than that.
So if we said the height of the cone is 3 times the radius of the cone, then we could just pick a radius that's somewhere inside of there, like a radius of 2,
Yeah,
and
so
then
that
plug in that.
may be helpful that there's a relationship between radius and height in that original cone. Maybe there is, actually don't know. But it's not really the volume of the cone that I'm trying to maximize. So in a sense, I don't know as I need that second equation. I need the volume of the cylinder is what I'm trying to maximize the volume of. And so that's the equation we need.
If we have that relationship between the height and the radius, we could subtract. So then we're trying to find how tall it actually is. So we could subtract that relationship from the top of the cone, because that's where it would hit the sides. Maybe I might not be explaining that.
I think I know what you're saying, but I'm sure other people are like, oh, I get it now. Like, but as an example, just to kick it off, does it make sense? You could say, well, I'm gonna say the radius of my cylinder is 2. Why did I pick 2? No idea, because I don't know what I'm doing. I have no idea what I'm doing. By the way, does it make sense that radius would have to be less than 6 for it to fit inside there? So I just picked 2, so that's pretty small. That's 1/3. My drawing doesn't match that very well. Should have probably made it match my drawing, but so I say, okay, so sort of I'm just going to say like 1. This is my first guess. So great, I'm almost there. It's like volume of the cylinder is pi times the radius squared, and now is when I like bump into a wall. And this is what Logan, I think, was getting at, is like, how am I going to figure out what the height is? Well, notice the height is like right there is where it hits the top, and that's not 18. And so the question is, heck, how tall is that? Notice this time I don't have an equation. Last time it was like a parabola. So I said, oh, I'll just plug 2 into the equation and it tells me the height. Well, this time I don't have that. How am I supposed to figure out what the height is of that? This is the part of this that's really creative. And that's hard. You could stare at this a while. You could end up having to ask somebody for help. You could end up punting, but this is not easy.
Could you find the slope of the slanted line and then make an equation for that, and then just use the radius or lack thereof as the x, and then the height as the y?
That would totally work. In other words, what Faith is saying is, back here we had this pink equation for that parabola, and that's what we used, right? And so she's saying, well, could we actually make an equation for that? Like the side of the cone is actually a line. So could we find the equation of that line and use that equation to, be able to plug 2 into, so to speak? So the answer to that is, yeah, that could work. I'm going to try her idea. By the way, that wasn't my idea. So I'm going to put the cone right here. Notice there's no XY axis here, so you can kind of put the cone any place you want. And this, where I'm putting it, might not be the best idea. But I'm just thinking, if I went, left 2, if I put in x is -2, then wouldn't that give me the height? So I sort of need this equation. I need that equation right there. So
x would have to equal x plus 6 because it's offset 6 to the left.
yeah, so what does it take to know the equation of a line? This is one way to do it. But I got to know the y-intercept. Well, based on the dimensions of the cone, what's that y-intercept up there?
18.
The height of this thing is 18, so that means I know this is 18. What's the slope of that line?
It's 6 over 18 up. Is it 1/2 or 1/3 or 3?
Yeah, isn't it 6
One.
over 6 here and 18 here? So it's a rise of 18 and a run of 6. 18 divided by 6 is 3. Good job, Faith. So there's an equation. This will do it. So I think the equation is y equals 3x plus 18. And again, that's for the left side, right? Not the right side, it's the left side. So that means if I put -2 in, since in my problem, based on the way that I drew this, I drew my drawing to go left 2. So that would be -2. So 3 times -2 is -6 plus 18 is 12. So it'd have a height of 12, apparently.
Unknown caller. Unknown caller.
So that's one option. That's a lot of work. So 12 times 2 squared times pi. Let me give you another option that's probably easier. And that's kind of proportions. So we said, let's find an equation. Good idea. But again, I'm doing this to illustrate because you can think, like you can reason about this stuff. The second method would be kind of using the fact that you have triangles in here that are proportionate. So for instance, and by the way, you'll notice this has a lot in common with the base idea about finding an equation for a line, but didn't we say this distance was 6 and this distance was 18? Like that's the proportion of the triangle that the cone is. And so then if I go in here with my cylinder, and I'll draw this a little more accurate at 2. So that distance right there is 2. Then one thing I could say is the proportion, the height of this right triangle to the base. So it's 18 to 6 in the red triangle. So I'll leave that in red. So I can say 18 is to 6 in the big triangle. What? Let's see. Well, I need the height in it. So what would the second one be? Maybe I better not use orange. Or use blue. As this height here, because that's the height I'm after, is to this distance. But don't we know that distance down there? What would that distance be?
More.
Yeah, since the whole distance all the way across this was 6, and we went over 2, then that distance is not 2, but 4. So I could say 18 is to 6 as h is to 4. So, and maybe while I'm at it here, I'll point out, didn't that 4 come from, if you will, 6 minus my guess of 2? Because later on, I'm going to want to not have to do this with 2 every time. So let's see, if I solve this for h, then I'd multiply the 4 up by 18. So that would mean h is equal to 18 times 4 divided by 6. That'd be 12. Hey, same answer I got before. That's good news. So then to kind of finish this first guess, this is really hard. I guessed the radius of 2. So v of 2 was pi times 2 squared times 12. So I had to work really hard to get the guess of 2 was no problem, but I had to work really hard to get the 12. So I got 48 pi, whatever that is. I guess I'll just write it as 48 pi. So there's a volume. Yeah, I should write it as a decimal because I'm going to have to compare that to some things later on. So I got about 150.8. Again, do you feel yourself saying, wow, I just kind of barely survived that? Like it was hard. I had to ask people for help, whatever. Sat there for an hour and stared at it. That was kind of hard. So I find myself wanting to like do another guess, if you will, just to kind of, do I get this? Like, is this working? Do I understand what the heck is going on here? I don't know. Barely survived that, you might say. So I'm going to hang on to this and again, make another guess. And so let's jump into a second guess for this. And maybe after 2 guesses, I'll say, okay, now I'm ready to do my math, not with 2. Remember, this was all focused on 2. We guessed 2. So I think I'll highlight that back here and say guess equals 2. So let's go down here now and try, I don't know, guess equals, I think I'm going to do 1. So that's going to make a really tall, thin cone, a guess of 1. So the advantage of Faith's idea to actually find an equation, that just means I can, go back to what we talked about here. Like I have an equation now, I can just throw in X. I can just throw in a number for that and get on my way. Or I could use proportions. I don't know which one to use. I guess I'll use proportions because I can see it here. But so just to draw a picture to make sure I don't screw this up, actually, I'm just going to copy the one above it.
Yours is almost an equation just because you wrote like the relationships alongside the numbers along the way. So you kind of step through it, seems
Right.
like.
That's exactly right. I mean, that equation and that proportion actually turn out to be the same exact thing. So the only thing that changes in this picture is just that guess becomes 1. So then I say, okay, well, then I'd say 18 is to 6 as H is to 6 minus 1, 5. So this distance in here be 5. So that'd be, H would be 90 over 6, which for some reason I can't do in my head. Hence, H is 15. So that kind of makes sense. If your cylinder is narrower, then it's going to get taller. So this was a smaller cylinder, smaller radius cylinder, but it got taller. So now I can say the volume of my cylinder, if I guess 1, is pi times radius squared times H. Well, that's only 15 pi, so that's kind of going in the wrong direction, you might say. My guess wasn't very good. 47. I'd like to guess one more, but I see the time is 9:19. So what I want to do now is say, could I go back and do this? Now, could I actually do this with letters instead of numbers? And it's not that terrible. What is supposed to happen? So for this third try, I'm gonna let my guess just be guess. So now the question is, can I do with letters what I've been doing with numbers? If I call this G, then can I say 18 is to 6 as H is to, well, what have I been doing? 6 minus G down there. So H then would be 18 times 6 minus G. My G's and 6's look too close to the same, divided by 6. Take a look at what that equation is, though. If you actually take 18 divided by 6 and you get 3, now you have 3 times 6 minus G, which is actually equal to 18 minus 3G. Notice how similar, I'm not going to say it's the same, and I'm not going to talk about the difference, but notice how similar that is to the equation that, I mean, it's the same equation effectively. It's just a question of, in our case, I looked at the left side. Remember, we looked at the left side of the graph over here, which was kind of a dumb thing to do. We looked at the left side, which means when we put in a guess of 2, we actually had to put -2 in. But in our case, we're just saying, well, look at the right side. It's the same exact thing. And then the slope, though, would be negative over there. So it'd still hit at 18, but the slope would be -3. And then your guess could just be +2 instead of -2. And so it's interesting that actually produced the same equation that the line equation was. And so now I say, okay, well, what's the volume of this thing? Pi times radius squared times height. Now we have an equation that we can take the derivative of and set equal to 0. So let me do that quickly. Again, I find myself thinking, I think I'm going to multiply that in. I'd rather not do the product rule. So if I multiply that in, I'd have 18 times pi times G squared, and then I'd have 3 times pi times G cubed. And so of course, what I'm interested in is, because I'm going to do this using calculus, is to take the derivative of this statement. So the 2 power rule comes down front, multiplied by the 18. The pi is another constant that just comes along for the ride. The 3 comes down, multiplied by 3. 3 times 3 is 27. 3 times 3 is 9. That's something I do a lot. 3, not 3 cubed, it's 3 times 3. G squared. And of course, I want to set this equal to 0. And notice this problem, because it has a g and a g squared, but it doesn't have a constant term. I could put this in the quadratic formula. 9, negative 9 pi would be a, 36 pi would be b, and 0 would be c. But in this case, I can just factor out a g. And maybe while I'm at it, I'll factor out a pi, since they both have that. I could even factor out a 3, but I think I'll just factor out a pi and a g and see if that's a good idea. So that leaves 36 minus the g, with 9 there, 9g. And so this one is g equals 0. Make it 0, but that's terrible. If g was 0, notice your cylinder, your green cylinder, has no radius, but it goes all the way to the top. So it's like super skinny, like a straw, but it's actually infinitely small. So that g equals 0 doesn't make any sense. But this one says g is equal to 4, and that's kind of cool. It came out an exact number, which means we actually could have guessed it this time. G is equal to 4, exactly. And just to kind of finish this really quickly, let's see if I try to draw this reasonably proportionately. Let's see, how did I do with that? Does this height look 3 times that length? I would say no, that looks more like double. So really should be more like this. Again, all I'm doing here is just checking my work and thinking, just to see, does this make any sense? So since the entire distance is 6, then 4 would be about there. So the cylinder we're talking about, if you will, is kind of a good balance. And that's what's kind of interesting about these questions, is it's kind of a good balance. It's wide enough, it's nice and wide, but it's not so wide that it loses all of its height. So max volume at G equals 4. So we got time to 3 problems today, but notice every one of them is different. Like getting one of them right didn't help you one bit with the next one. And that's the way it's going to work in life. And so, and again, I'm going to give you practice problems and so forth. There's a good chance one of the ones we do in class will be one of the ones on the test. It's not like I'm going to just make up a totally separate question. So you will have seen it before. But I just think these problems illustrate how challenging it is to write your own equation, and how you've got to, know some geometry. In this case, we set up proportions, or maybe like Faith realized, oh, we need to have an equation, and every problem is so different. So anyway, there's a start. You might wade into the homework assignment. You have all kinds of time. It's Monday. You might wade in and like do the ones that you can, play around with them, and certainly at the end of tomorrow's class, because after that, in a sense, I've taught you everything that we have time to talk about. I guess you could say, well, I still don't really feel like I'm very, very good about number 6. Can we stay after and give me a hint on that question? So the only thing I want to do tomorrow is kind of, practice some more problems, but I also want to get money involved. In other words, one of the problems I remember in your assignment, which is kind of a good one, is like you're trying to make a can that's a cylinder, but the sides are made out of a material that doesn't cost as much as the top and the bottom. So you're trying to make it cheaply. It's not just get the area small. You're trying to get the money small, if you will, to make something. And so can we get money involved? So all kinds of cool questions. We could talk about this for a week, just because there's so many neat questions, and it takes practice and it's hard. So, all right, shut up. I will see you tomorrow. Stay after as usual if you like.